Okay, let's look at properties of the Fourier transform. We'll have properties similar to those we derived for the Laplace transform and the Z transform. The notation I'll use is in the time domain we have we'll call our function x of t, and it has a Fourier transform of x of omega, and I'm interested in the Fourier transform of a time-shifted version of x of t, and use the definition of the Fourier transform actually to show that the Fourier transform of the time-shifted version is equal to the Fourier transform of the unshifted function, then times just e to the minus j omega t0 times the time shift. So just a simple example. So we've got e of t is, x of t is e to the minus 2t, u of t minus 4. Okay, I have to do a little algebra trick to get a t minus 4 here, because this is a function that first becomes non-zero at t equal to 4, so it's a time-shifted function. But I've got to get the time shift everywhere. And I'm going to pull out the e to the minus 2 times 4, so that'll be e to the minus 8, which is just a constant. And I've got e to the minus 2 t minus 4 u of t minus 4. Okay. And then I'm going to take the approach that I'm going to define a new function, w of t, as e to the minus 2t u of t. Because I see that embedded in here, x of t is going to be related to a time-shifted version of w of t, but w of t has transform w of omega equal to 1 over 2 plus j omega, and then based on the definition of w of t and x of t, I've got this relationship in the time domain. X of t is just e to the minus 8 times time-shifted version of wt. Notice that if I substitute t minus 4 for t everywhere it appears, I get this portion of x of t. So this means that x of omega will be equal to e to the minus 8 times w of omega. And then I've got my time shift here from this time shift property. It's e to the minus j omega 4. Notice and the property is written as minus t0. I've got the minus t0 that appears in the exponential, so the minus 4 appears as the minus 4 here. I could rewrite this as w of omega e to the minus 4, factoring out a 4. When I combine the exponentials, I'll have minus 8 minus j omega 4. I can factor out the 4 and write this as 2 plus j omega. Okay. So finally, using w of omega, I have the Fourier transform of x of omega as 1 over 2 plus j omega times e to the minus 4 2 plus j omega. Okay. And probably what you'll want to be thinking about is taking inverse transforms. And if I see a multiplication by an e to the minus j omega times a constant, I know that's going to correspond to a time shift, so I'm going to factor that out. Here what I would do is I see this e to the minus 8 term, which is just a constant, and so I'd pull that out as well, and then I'm left with the e to the minus j4 omega, which is a time shift. And so that's the procedure we'd use to take the inverse Fourier transform of this function. Okay, time scaling. If I have a function that's equal to x of at, then the corresponding Fourier transform of that function is 1 over the absolute value of a times the Fourier transform of my original function with argument omega over a. So everywhere omega appears, I would replace omega with omega over a. For a greater than 1, x of at is a time compressed version of xt, while this would be an expanded version of x of omega. So it's another demonstration of that property that we talked about before, that the smaller the duration in time, the wider the width of the spectrum in frequency. Other property, frequency shifting, or modulation. It's this property that's the basis for all wireless communication mechanisms, everything from AM radio to HD TV and satellite and cell phone communication, as you'll learn in a subsequent communications course. But this says if we have a function x of t and multiply it by this complex exponential, that results in just a shift of the spectrum in the transform domain. Using Euler's formula, we can go on to show that this is typically what's done in communication systems, that if we multiply our signal by cosine omega 0 t, that results in a shift of the spectrum to the right up to omega 0 plus a shift in the spectrum to the left to minus omega 0. So just as an example, let's assume that x of omega looks like this, and then I'm going to multiply that by a sinusoid with frequency omega 0. Then based on this property, I'll have this function shifted to the right by omega 0. It will have half the height because of this factor 1/2. And then I'll also have the function shifted to the left to minus omega 0. I still have the required complex conjugate symmetry, actually, that's necessary for this product to still be a real function. So, and then this is the Fourier transform of x of t after multiplying it by a particular sinusoid. In the case of wireless communications, this frequency in hertz is up in the megahertz range, or hundreds of megahertz range, or even up in the gigahertz range for satellite communications. And then a couple other properties. Duality. And this actually doubles the size of our table, although it's one of the more confusing properties. Again, we use the uppercase x to represent the transform function, and the lowercase x to represent the time domain function. this says, now, if we have a time domain function that matches one of the patterns in the Fourier transform side of our table, then its corresponding Fourier transform is 2 pi times the time function with minus omega substituting for t. So again, it will essentially allow us to look for time functions on both sides of our transform table. Now, this property actually comes from the similarity between the Fourier transform integral and the inverse Fourier transform integral. You know, they differ by a minus sign and a factor of 2 pi if you go back and look at the definition. So, as an example, let's say we're going to find the Fourier transform of W of t is 2 plus jt squared, and I look through my table of Fourier transforms in the book. There's no similar x of t in the table, but I see this entry. I see x of t is equal to t e to the minus 2t u of t, and corresponding transform is x of omega is equal to 1 over 2 plus j omega squared. Okay. And I see that the x of omega function matches my time domain function with t substituted for omega. So we can apply this duality property to say then that if Wt, if I substitute t in for here, I have this. So the Fourier transform of W of t, W of omega, is going to be equal to 2 pi. Then I take the time domain function, the function on the left-hand side of my table. Now I'm going to substitute in minus omega everywhere t appears. So minus omega e to the plus 2 omega, and then u of omega. So this would be the Fourier transform of this particular function. And if I were to sketch, in this case, it's entirely real. If I were to sketch the spectrum, actually I can just sketch it so it's entirely real here, because of the multiplication by u of omega here. This is only going to be non-zero. Oh, I'm sorry, that should be minus omega. I didn't actually substitute in negative omega for t everywhere, so it's minus omega. So this is only going to be non-zero for negative values of omega. And then for those negative values of omega, this is a decreasing exponential. Also, because omega is negative, the negative omega, this is going to result in a positive value. So, this thing's going to look roughly like that, something like that. The exponential for increasing omegas, as omega becomes more negative, this term is going to go to 0. Okay. And probably the most important property to us, because it allows us to find the output of our linear time invariant systems for a given input. We know that we can find the output by convolving the input with the impulse response. The Fourier transform of this convolution is just multiplication. So we multiply the Fourier transforms of the input signal and the impulse response. We know that since y of t is x of t convolved with h of t, find the output, then again the Fourier transform of the output is just the product of the Fourier transform of the input and then the Fourier transform of the impulse response, which is the frequency response of our system. So we can use this then to find y of t by taking the inverse Fourier transform of this product. Okay. And two other properties quickly. Differentiation. The x of dt transforms as j omega x of omega multiplication by j of omega, and so an nth derivative of x with respect to time transforms as j omega to the n power times x of omega. And finally, integration. Where if we're integrating from minus infinity to t of x of tau d tau, corresponding Fourier transform is 1 over j omega x of, 1 over j omega x of omega plus there is an impulse due to any DC component x of 0 times delta omega. And notice this is the Fourier transform function evaluated actually at omega equals 0. So we'll have this term present unless the Fourier transform of x of omega is 0 at omega equals 0, indicating it has no DC component. You'll find these properties as well as others in table 7.2 in your textbook. They're also provided on the back side of the handout I will give you in class.